Word and share screen. Okay. So how do we train recurrent neural networks? So I want to learn these weights, the WHI, HY, sorry, the WHH and WHX. So I have some training data. These are typically sequences, a set of sequences. So for example, the training data could be a set of spoken pieces, so speeches and their corresponding text, for example, or a set of sentences in German and their corresponding English sentences. So I want to use this training set to train the neural network, the recurrent neural network, and this is done through gradient descent as before. What is known as, it's just a fancy name for it, backpropagation through time, because I'm doing this through time. So what happens is I pass one input sequence. So let's say I'm doing speech recognition. So I'll pass my spoken speech, my one instance of it, through the recurrent neural network. So that will give me, the hidden state. So I can compute, I set the weights randomly. I set the weights at random, so that would give me some hidden states, and that would produce some output because I have the WHI, HY, the WHH, and WHX, so I can get some output. Okay. Of course, these words would be very off from what is actually spoken because the weights are done. Yeah. I compute the loss. So what is I know the correct word that was spoken because this is training data. I see what is the difference between what I've predicted and what is the spoken word. So for instance, I can do softmax and compute, cross entropy error, and then use this to backpropagate. Why backpropagate through time? Because this one depends on all the previous steps, all the words that have been spoken until I've reached here. This one depends on all the previous ones. So the error here is backpropagated through time all the way till the first step. Yeah, it's the same weight matrix, but it's backpropagated through time steps. We're doing, let's say you're doing a loop as you're passing through the input sequence. You're in the backpropagation, you're doing a loop in the opposite direction. Yeah, so you keep looping and updating the weights, keep looping and updating the weights until you reach the beginning of the instance. Yeah. So you do a forward pass through the entire sequence to compute the outputs, compute the loss, and then backpropagate the loss through the entire sequence to compute gradient. Okay? More or less, this is what you need to know, right? The intuition behind this. You can look at the code, right, and the assignment and see how this actually works. And this is very intuitive. Okay? So let's see a concrete example, and then I'll stop there and continue on Tuesday. We'll continue on Tuesday. So language models, it's a very important application. The character level language model, meaning the goal is to generate meaningful text. So what was one of you was saying, this thing of detecting what is the word based on what I'm typing is some sort of language model. Yeah. So given a sequence of characters, predict the next character. So that's the goal of the language model. I give you a sequence of characters. Let's say for example, UPLOA, right? Let's say I'm typing this in WhatsApp, UPLOA. What do you expect the thing to detect next? What is the next character? Any thought? Huh?
D, so the word is upload.
Yes, the word is upload. Exactly. Okay. So this is what is a language model. Given a current set of characters, character level language model, given a sequence of characters, what is the next character? Yeah. So given a vocabulary, a set of characters, estimate the probability, YT, so the current character, given all previous characters, Y1, Y2, until YT minus 1. So let's consider the vocabulary to be the English alphabet. So we could build these probabilities. So a language model is a probability distribution. Yeah? So probability of A given SU is equal to 0 because you don't expect A to appear after SU. There's not a lot of words in English that have SUA right sequence. But there is, for instance, B after SU is 0.2, so it's a little bit higher because you have the word sub, right? Is a valid word or a part of a word in English, yeah? Again, C, so C after SU has some probability and so on. You're computing the probability, including the probability of the full stop. So ending the word with just SU. So a word with just SU, nothing else. That's what I mean by probability of full stop given SU. Okay, so if you have this probability distribution, I can pick the maximum one. So after I've read SU, I can pick the maximum next character, right, based on this probability distribution. Yeah, in this case, it would be either B or R. Yeah, so I output either B or R. In reality, what happens is I use sampling and we'll see what this means. So that's not deterministic. Not every time I type SU, I always get the same prediction. It does some sampling based on what is these probability distributions. Yeah, but that's the idea of a language model. You understand it? It's predicting what is the probability of a given character. If I'm doing character level language models, what's the probability of a given character given what I've seen so far. If I'm doing word level language model, it would be given a set of words that I've seen so far, what is the probability of the next word? And that's used in, for instance, speech recognition.
Sir, can you repeat the last thing about the probabilities? My internet crashed.
So you estimate these probabilities. Your goal is to estimate these probabilities or learn these probabilities, right? Where the probability of A given SU, and you learn this from data. From how many times did you observe A after SU and how many words? Once you have these probabilities, now given that the user has typed SU, you want to predict immediately what is the next character to type it for him. Yeah. So you can predict that it is either B or R because these have the highest probability. Yeah. That's if you're doing a greedy algorithm, but that's deterministic. That will always output sub or SIR every time you type SU. So to make this a little bit non-deterministic, you typically do sampling. So you sample using this probability distribution. So not all the time you're outputting B, not all the time you're outputting R, but most of the time you're outputting B and R because they have higher probability than the other ones. Yeah, this is what I said. Let's see an example.
Okay, thank you.
Okay, you do this, so given, again, repeatedly, for given a particular sequence, sun, what is the probability of the letter A, what is the probability of letter B, and so on. Okay, so let's see how does this work. How do I train a character level language model? Let's assume that my vocabulary just is 4 characters, H, E, L, and O. Okay? So the training data is a set of valid words using the vocabulary. So I have a set of words that I've gathered, right? A lot of words that are valid words using the vocabulary. For instance, hell, hello, he, I don't know what else, right? But basically, whole, right? And so on, right? So these are the words, valid words in the vocabulary in English that are used, that use these 4 characters. Okay, so that's my training data. I have a lot of these words. So I'm going to train the neural network, the recurrent neural network, as follows. Yeah. The input first is going to be a 1 hot vector. What does it mean, 1 hot vector? It means that every character is represented as a vector of 4 because I have four characters in my vocabulary. Yeah, so I have a vector of 4. H is represented at the first one, E is the second, and L is the third, and O is the fourth. So the first one, I want to represent, let's say the sample input and word that I'm training on currently is hello, yeah, or hell, H-E-L-L. Okay, so the input is gonna be 1 0 0 0 because I have representing the character H, yeah, and it's 1 hot vector. For E, it's gonna be 0 1 0 0. For L, it's gonna be 0 0 1 0, and for L, it's gonna be 0 0 1 0. Because this is how. If I was O, for instance, it would be 0 0 0 1. But I have H-E-L-L. So this is the input sequence. I'm going through the word hello and trying to train the language model. Okay. So I set the weights, right, randomly. So WXH, WHH, and WHY would be set randomly, initialized randomly. And I'll be able to compute the hidden states, right? H1, H2, H3, H4 based on WHH and WHX. I'll be able to also compute the output, right, based on WHY, because I have the hidden states, multiply them by WHY, yeah, and that gives me the output. Okay. Now I know, right? I know that my word is hello. So given age, let's see what I predicted. So I predicted here, right? Basically, I would have predicted that it's L, that it's O, because this has the highest, this is a softmax, remember, right? So this has to pass through a softmax. So I will normalize these values to turn them into probabilities. And so most likely I will predict, right, the letter O as the next letter given age, because this has the highest activation, 4.1. So given age, I would have predicted O as the output, right? But I know that the correct output is E, so it's 2.2, right? The one corresponding to 2.2. So I made some mistake. I backpropagate this error, okay? So output is softmax probabilities over the vocabulary, and the loss is cross-entropy error. Go back to softmax and multi-class classification when we talked about neural networks. Remember what cross-entropy error is. Okay. So basically, if I have set the weights according to the current values, whatever the values is, I would have made a mistake on the first prediction. I would have predicted O, and it has to be E. So I have to backpropagate this error. Okay. Also for this one, I would have predicted it as most likely O, where it has to be L. Yeah. So I backpropagate this error through this and through this. Here backpropagate again the error, whatever error I make through this, and backpropagate the error through this. So I compute basically the error and backpropagate it through these connections. Yeah. Okay. And this is how I change. Now I take the next word. So this would improve the weights a little bit, because I would try to improve the weights so that I output E when I read this word, when I read the character H, and when I read the character H and E, I output L. So I update the weights in such a way so that I get these correct. I get the outputs, the target characters, correct as what I've predicted based on the softmax. So that's what I'm trying to update the weights to. Okay, and now I pass it the next word and the next word, and I keep updating the weights over and over and over. After a while, the weights would have learned, right, what to output if it has seen H, and what to output if it had seen HE, and what to output if it had seen HEL, based on the probabilities that it has learned. Yeah. So at this time, let's say this is the input character. So I'm reading now the words, or typing these words in WhatsApp, these characters in WhatsApp. I'll pass it through the WHX. This is fixed now. I've learned it. I've learned the WHY and the WHH. This is the model now. So all I have to do is just multiply to get to the hidden states, get the output layer, and then do softmax to normalize and turn these into probabilities. What has the highest probability here? Which one?
O.
O. So I should, if I'm using the maximum probability, I would have output O. But what I do is I do sampling, as I told you, right? Sampling based on these probabilities, so that it's not deterministic. Not every time I type H, it predicts O. Yeah, it will. I want it to predict sometimes O, sometimes E, sometimes. So based on these probabilities, so I sample E. So I got
This,
yeah.
sampling, you mean like we choose a random
random letter based on,
and we see the highest probability.
Yeah, based on this probability. So a random letter based on this probability. So most of the time you will pick O, but also you will pick E sometimes, and you will pick L sometimes, right? So this is what I mean by sampling. Yeah.
Okay, thank you.
Right. So let's say I did sampling and I got E. So now I pass E as the input sequence next, and I pass it through the network. So the WXH, the WHY, and the WHH, and then I get the probabilities here, and that tells me the next character is. I sample and pass it to the next step, until I get the next output, and I sample, and then I get the next output, until I get a dot. Once I get a dot, I stop sampling and output this as a word. Yeah. So I also have a probability of the dot. Here I didn't show it, but I usually have a probability of the full stop as well, meaning that I've ended one word. I've predicted one word. Okay. So this is more or less character level language models. Let's see an application of it, and I will stop here. So this is, you can look at this code. So I encourage you to play with it. It's really cool. So you can just download the code, the notebook, and see what they have done. They did train a character level language model on all Shakespeare's plays. So they took all Shakespeare's plays, and trained this architecture that I've just told you. Plus, sent words by words by words by words as training sequences, and try to learn right probability distribution of the characters. Yeah. And once they did this, they managed to generate new plays for Shakespeare. This is just examples of how they look like. They're not very coherent, yeah, but they sound interesting or sound a little bit Shakespearean, if you wish. Yeah. So if you look at this, the first one says, "Alas, I think he shall become approached, and the day when little twain would be attained into being never fed, and who is but a chain and subject to his death, I should not sleep." Yeah. So somehow it doesn't make perfect sense, but they are still cool. I mean, this is automatically generated. Yeah. We'll try to. I'll think about it. Maybe I'll try to give you in the assignment where you do this on tweets. So I give you a data set of tweets, and then you build a language model that learns from these tweets. And so when it generates new tweets, it has the same flavor or the same probability distribution or language model as the trained tweets. So let's say you train on Trump tweets, then you can generate new tweets that sound like as if Trump has generated them. That's what a language model is. Yeah? Language model means you're modeling the language of somebody or of some corpus, yeah, if you wish. Yeah? So this is what we do in language model. Okay, questions? Find this difficult?
Not really, but we have write code to see how it works.
Yeah. The code is really relatively straightforward. Once you've got familiar with neural networks, the first assignment, you will really be able to do all of this seamlessly without any issues. Yeah. So the same set of hyperparameters. You have learning rate, have number of layers. You have basically activations and so on. So it's all like, what is the optimizer? It's almost the same set of hyperparameters. It's just that the architecture is a little bit different. Yeah. So the core architecture is different. That's all the biggest difference in this. Okay? All right, folks, then we talk on Tuesday. I'll post the slides or the lecture recordings as soon as I can. Okay, good luck with the next assignment.
Thank you, sir.
Yeah, bye-bye.
Thank you, Professor. Bye.
Yeah, bye. Bye, guys.
Good luck with your meeting, sir. Bye.
Thanks, bye-bye.